Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. We're talking on light and we've started discussions on refraction of light. We're going to move into a major area of refraction, and that is to deal with what are typically referred to as lenses. And it has a number of applications of its own. So, we will look into what lenses are and how they are put to use. A dense, transparent medium with a curved surface acts as a lens. It may have just one curved surface or two curved surfaces, and they could be of different types. It could be made of glass, it could be plastic, it could be polymers, which are used, which are transparent in nature. If it's a curved surface, it must have a radius. So one curved surface has a particular radius R1, and the second one has another radius R2. But the lenses could be something like this also, or it could be a flat surface just like this, or it could be just like this, and these are all given specific names. Why it causes bending of light and images is something that we need to understand based on what we have already discussed last time. We've talked of prisms, and I told you when I talked of prisms that a prism has an angle on top, angle at the apex, and any ray parallel to the base will be bent towards the base when it passes through a prism. Now, if you look at any lens, it can be made up of a number of prisms. The one right here is as good as two flat surfaces, so its angle on top is practically zero. And as you start taking the next and the next and the next and the next and the next bit, the angle starts becoming more and more till you reach the topmost point, which is angle A at the top of the lens. Same thing would happen below also. So I'm talking of a lens whose circle is like this, but I'm looking at its cross section, which is like a set of prisms with different angles. Now, if a ray of light comes right from the center along the axis of the lens, for it, the two sides are as good as flat. And so the ray goes straight through. There's no bending at all. But the ray on top of it will go and then bend a little bit downwards. The next one a little more, the next one a little more, the next one a little more. The same thing would happen for the part below also, and the rays would start moving upwards in that case, towards the base again. And the result is, mathematically, this curved surface will cause all those rays to meet at a certain point on the axis. That point is known as the focus or the focal point. And if you take the center of the lens and measure the distance up to that particular point, it is known as the focal length of this particular lens. Realize that I'm talking of light coming from this side. So if the light is coming from the opposite direction, it would come to focus at some point this side. So there are going to be two focal lengths for any given lens. Now, what are the type of lenses that we talk of? It's a boundary of curved surfaces, and it is named in different manners. If both the surfaces are like this, bulging in the center of this nature, it is known as a biconvex lens. If it's a flat surface on one side and a bulging one on the other side, it is known as a plano-convex lens. The surfaces could be like this, the lens could be something like this, and then it is known as a biconcave lens. And it could be only one surface of this sort with a flat surface here, and then it is known as a plano concave lens. That doesn't end. I could have more bulge on this side and less bulge on the same side like this. The effect is that it is thick in the center, and so it is dominantly convex. So it is known as concavo convex. Or it could be a situation where it is bent more inwards and less outwards. So it's thin in the center and thick at the edges. That is known as convexo concave. Just realize that they are not really flat and straight, but there are so many possibilities. And when you look at your glasses, you will find that they are not like normal lenses, they are curved and there are curvatures on both sides. So it could be a lens which is thick in the center but curved, or it could be thin in the center but curved. These are all the possibilities that are there. There is one more important way that you can identify lenses, and that is based on what the lens does. It's possible that it can cause light to come to focus at one particular point, like what I just told you some time back. And such a lens is known as a converging lens. A converging lens brings light to focus at a particular point and it can produce an image at that particular point. A biconvex lens is a converging lens. A plano convex lens is a converging lens. A concavo convex lens is a converging lens. Any lens thick in the middle is a converging lens. It brings light to focus. But think of the other possibility. If it's a concave lens, it's going to be like this. And then those prisms that I talked of are going to have maximum angle in the center. And as you go towards the edges, the values will start becoming different. So you would find that the behavior of a concave lens is reverse. So the ray of light that comes, since the base is on top, the ray would come like this and bend upwards. The next ray will also bend upwards. The next, only the central one will go right through. So when you look from the other side, the rays will appear to come from one particular point, and that is the focal length of a concave lens. So what does a concave lens do? It spreads out light. So it is called a diverging lens. So biconcave lens is a diverging lens. A plano concave lens is a diverging lens. A convexo concave lens is a diverging lens. They are very easy to identify. If you look through a concave lens, you'll find that everything beyond is erect, but it is diminished in size. And that's whatever distance you do, it's going to remain the same. And that then is a concave lens. But a convex lens can produce magnified images and diminished images and so many other things. I'm going to come to that too. Now, once you know that light can be brought to focus, how do you know whether a lens is good or bad? What decides on the power or the strength of a particular lens? If the rays bend more and come to focus, they'll come to focus closer to the center of the lens. So the focal length will be small. So if the focal length is small, the lens is said to be more powerful. Also, there is another way of calling this in terms of numbers. And that number is something that is known to us. It is known as diopter. So, and it is represented by capital D. And this is also given positive and negative signs. If it's a converging lens where the light actually comes to focus, it is said to have a positive diopter value. And if it's a diverging lens, it has a negative diopter value. Actually, we hear this very often. When you go and buy your glasses, then you are given a number, and that number is nothing but this diopter value. So when I say diopter value is 1, it is 1D. And if I say it is -1, it is -1D. That's what it is abbreviated. That's all. But that's not enough. I must know what the focal length is. And that's also pretty simple. The diopter value is equal to 1 upon the focal length, which is measured in meters. Or the other way around also. The focal length in meters is the reciprocal of the diopter value. Let's try in terms of something very simple. Let's try and make it in terms of some simple numbers. Suppose diopter value is +1. Then the focal length will be 1 upon 1 meter. That means 100 centimeters. So if the diopter value is 1 plus 1, it's a lens, whichever type, whose focal length is 100 centimeters or 1 meter. If the diopter value is +2, then the focal length will be 1 upon 2. But it has to be converted in terms of meters. So it will be half a meter. 1 upon 2 is half. And half is 50 centimeters. So when the diopter value is 2, the light comes to focus at 50 centimeters. So it's a stronger lens. So if the diopter value is +5, the focal length will be 1 upon 5. That is 1/5 of a meter. That is 20 centimeters. So that's a still more powerful glass set of uh, lens. And these are the numbers that are given to the various glasses that we wear. How they are positive and negative, I'll tell you when we talk of actually how the eye is to be corrected. But the numbers could be negative also. So if the value is -4 diopters, it's 1 upon 4 of a meter, that is 25 centimeters. But it is minus, which means it's a diverging lens. And that diverging lens is of 25 centimeters. So that's how a power of a lens is measured. Just to give you a hint, if you put two different lenses together, one of 4 diopters and one of 2 diopters together, the total value will become 6. And if one is +3 and the second one is -2, the effect will be +1 and so forth. It is just simple addition when you put the lenses together. So this is how power of a lens is used. So it's quite obvious that if the power of a lens is more, the focal length will be pretty small. And now, once we now have this basic idea of how the lens looks, what is its focal length, we need to find out how it can be calculated and measured. And how can you make a lens if of a desired value? To make a lens, there is a particular formula. It is known as lens maker's formula. And it depends upon what is the material. Effectively, what is the refractive index of the material? How much is the radius that you want on the two sides? And then you can calculate the value of the focal length that you will get. So it can be calculated and it's a standard calculation. I can give you the equation. It's pretty simple actually. It is 1 upon focal length is equal to refractive index minus 1 multiplied by 1 upon R1 minus 1 upon R2, where R1 and R2 are the two curvatures. Let's keep that aside. It's pretty simple. It can be calculated. That's all that we need to know. So a lens can be designed. And so lenses were made for a variety of purposes once their use was known. And the simplest and the most important application that started off was to look at any object through a lens. And when you looked at an object through a lens, it appears to be magnified or it appears to be big. So if you are using only one lens of this sort, it is known as a magnifying glass. And in technical terms, it is known as a simple microscope. A magnifying glass must have two basic properties. One, it must be big enough for you to look through. So its diameter or radius or the opening, which is known as aperture, must be large, and it must have a short focal length, maybe about 5 or 10 centimeters is the value of the focal length that must be there. And in this case, it is known as a magnifying lens. And where is it used? Uh, the- there are two or three very simple uses that we always know of. You always talk to people who look at the lines on your hand and palmistry. So the instant you talk of reading your palm, you take a lens and look how the lines are. So you look at the lines because they get magnified by using a single lens. There could be situations where the focal length is still small, somewhere between 1 or 2 centimeters. If it is 2 centimeters, it will be plus 50 diopters. It's a very strong lens. That lens, what it's done is it's made in the form of a small disc, and it is fitted in a tube of metal, and that's hooked on to your eye here. And that's the one that the gemologists or those who repair uh, watches, etc., watchmakers, they use this lens that is attached. They hold it in their eye and look at the facets of a diamond or any particular object, extremely small, minute objects, or extremely small screws to check up the movement of small watches. So these are all very small, and so you use an attachment of this sort. Since its focal length is very small, it gives you a very large image when it is held very close. There's only one drawback. Even lenses have defects, and these defects result into the sides getting bad. And there is one more problem that I won't talk to you today. That will be next time. Now, let's go one step further. If I use more than one lens, then this problem of distorted images, etc., could be removed. And there is a limit to the amount of magnification that you can see. So if I want to make things much, much bigger, I need to use not one, but a combination of lenses. It started off with combining two lenses, and that resulted into the second area that I'm going to talk of today, which is probably more important today, which is what telescopes are. Tele is distant. Scope is to see. So to see objects that are very far away, what was designed was known as a telescope. I'll go to the history a little bit, and it's very interesting. It is said that a French lens maker, while making lenses of different sizes, held two lenses in front of each other and was just looking around. And he suddenly realized that the objects that were very far off appeared very close and quite magnified. And that's how it is said that telescopes triggered on. And once this was known, they started looking at designing these telescopes. So they were first designed to look at distant objects. The objects appear magnified. How much bigger? The lens that faces the object that is to be seen is known as the objective, and the one that is close to your eye is known as the eyepiece. So if you take the focal length of the objective and divide it by the focal length of the eyepiece, it tells you how much bigger the object appears. So if the objective is of 50 centimeters focal length and the eyepiece is of 5 centimeters focal length, then the ratio is 50 upon 5, which is 10. So the object would appear to be 10 times bigger. There was one problem. The way this works is the objective makes an image inverted of the object, and then the second lens, that is the eyepiece, is very close to this image. And so, like a reading or a magnifying glass, it produces a virtual magnified image of that particular object. So, first you get one image, fairly good enough, and then use the second lens. Now that the object is very close and magnified to some extent, you magnify it further. And what you get is a telescope that works. If the object is at infinity, the image will be obviously formed at the focus, and then you would be able to get that ratio that I just talked of, which is known as the magnifying power of a telescope. Focal length of the objective divided by focal length of the eyepiece. There is one hitch. I'll come to that first. And that is that the image is inverted. So if you want to use it uh, to see an object that is far off, a ship that is far off at the sea or so forth, there's no point in seeing an inverted image. So they put one more eyepiece beyond it, small size, which again inverted the image. And this then gave what is typically referred to as field glasses. But then people said it started getting too long. So you see all these in all these films and so forth. You see the pirates looking at with long tubes and so forth. So they used a couple of mirrors to reflect the light and reduce the total length. And instead of closing one eye, they used both the eyes and made a pair of them. And that became what is commonly referred to as a binocular. Ocular is associated with the eye. So bi is two. So you have one eye which has one image produced, and the second eye produces. In the second eye, you have the second image produced. And like what I told you last time, if you use a pentaprism inside, then you don't need to put an additional lens. The process itself will result into one reversal, and that will give you an erect image. And that's how prismatic binoculars are made. There was one more intermediate step, and that was instead of using to get a correct image, what you need to do is to use not convex at both ends, but the objective was convex and the eyepiece was concave. And these two together also result into something very similar. So when you look at toy binoculars or cheap binoculars that you go to see some sports event or something, very compact ones, those are the ones which have one convex and one concave mirror. I'm sorry, concave lens. So one concave lens and one convex lens. This is how telescopes started off. But I told you I'm going to tell you a very important associated concept. People started looking around, but there were very few people who sensibly thought of turning the telescopes to the sky. And so a lot of observations of what things are in the sky were made. And the person who did that to a very large extent was Galileo Galilei. And he turned the telescope towards the sky. There are two problems that are quite obvious. The objects in the sky are very dim stars. You can't see anything at the daytime, so it has to be at night. If you can't look at the sun through a telescope, you won't be able to see anything later on. So, so you need to look at objects at night. The quantity of light is very small, so the opening or the aperture has to be large. So you need to have a large lens that will gather more amount of light. But if it falls on the side and gets reflected, the image is going to be distorted. So all these telescopes are painted black inside. And then the eyepiece can be adjusted suitably to see an object very clearly. Now, what did Galileo do? He looked at so many things, and when he looked at Jupiter, he found that the telescopes then were not very powerful. They could give a magnification of about 20 or 30 times, that's all. But as it is, the star is very small. You can hardly see it, and you can just look around and see. Okay, this is Jupiter. So you could see the red spot and so forth. But he found that there were four small stars that were very close to Jupiter. So he could see the like shine of Jupiter and four more dots close by. When he looked the next day, he could see only three of them. A couple of days later, he could see only two. Then he could again see four and so forth. So he realized that they were drifting around. And then he put two and two things together and realized that these were going around Jupiter. The instant they went behind, you couldn't see them. And they came in front, and again you could see them. And then their movement was much more than that of Jupiter. And Jupiter itself seemed to have these moving around. And he identified them as the moons of Jupiter. This final spark of what was understood is a 1 second job, but it changed a lot of things. It proved that there are moons that go around other objects and that those are not going around Earth. And till that time, old Greek Ptolemy's concept of what is commonly referred to as geocentric Earth. That means Earth is in the center and everything goes around it. That idea was very strong. There was another person called Copernicus who did some calculations, so many other things, that was putting up a theory saying that it is not the Earth that is at the center, but it is the sun at the center. One sighting of Jupiter with its moons going around was an experimental proof. There was no need to do any calculations. If this is what is happening around Jupiter, it is obviously happening around Earth. So Jupiter is tracking down, moving around sometime in time. So obviously everything is not going around Earth. So it's going around something else. And that something else is nothing but the sun. And that's how this geocentric, geo is Earth, Earth centric idea was scrapped. But scientists always face a lot of problems. And he couldn't fight with the church because the church believed Earth to be at the center. So he had to, Galileo and even Copernicus, they faced a lot of trouble. In fact, they had to give up their ideas of saying that. But then it's like you can't cover your eyes and hide the sun. The truth had to come out, but that came out a little later. But that's the situation. One vision of Jupiter, and there was a direct proof of the sun being at the center of the solar system. This telescope is a major object that is used to see things in the sky. The trouble is the stars are so small, so you can't keep looking at them. By the time you look at them, if you have tried, it's very difficult. So it has to be mounted. So all astronomical telescopes are mounted. And then there is a mechanism to track down a particular star if it is a more sophisticated type of a telescope. Telescopes basically are of two types. One is the one that uses lenses, objective as a lens. There were some problems that arose because of lenses, which I'm going to come to as I go into the next topic next time. Uh, but this problem could be overcome by using mirrors. How is another story. I'm going to come to that also. Uh, and so you have what are known as reflection telescopes. All major telescopes throughout the world today are all reflection telescopes. Even Hubble, the telescope that we talk of, is a reflection telescope. And these telescopes are very powerful and they can produce very large images. The biggest one that we know of is, you must have read and talked of this and heard about this, is known as the one that is known as the Wilson telescope on top of Mount Palomar in the US. There are a few things that we must link with the information associated with telescopes immediately. First, if there is stray light around, you can't see all those galaxies and nebula and uh, other aspects in the sky. So you must go to a place where there is no ambient light around. Best place is to go on a mount on top of a mountain. So the whole observatory is built on the top of a mountain. The whole thing is enclosed within the structure so that there is no ambient light coming from any side. And you need to see a particular area and decide on which part of the um, sky that you need to see. So there is a dome, it has an opening, and the telescope is fitted within the opening, which can move like this, and the whole system can turn around. So you can adjust the system to any particular direction. So all this mechanism is the one that is used for every major telescope. Just to tell you, this Mount Palomar telescope has a 200-inch diameter. 12 inches is 1 foot. 3 feet is practically 1 meter. I'll leave the calculation to you to decide how big the diameter is. Of course, let me also remind you that it's a reflecting type of a system. And the whole telescope itself is 14 and a half tons. This tube. But it has to be moved, and it has to be moved precisely in fractions of degrees. And the whole assembly weighs close to 500 tons. And there is a tracking mechanism which are typically referred to as servo motors, which are the ones that are used to drive. There are special cameras that are built in to take the necessary photographs. And that's the one that gives you so many beautiful images. I'm sure many of you all must have glanced at images through telescopes. I'm going to dampen, I'm not sure whether I should say this, but you might be disappointed when you look through a telescope the first time. If you look at the moon, fine. But if you look at stars, you would start wondering, oh, is that what I'm going to see with a telescope that costs $5,000, $10,000? Is that what I'm going to see? The reason is the photographs that we see are by the best of the systems, and they're pretty well taken and specially designed. There are a lot of problems that can arise. I talked of different layers in atmosphere, and they are drifting around. So the images that you see are not going to be perfect. That was one of the reasons why telescopes were sent into space, and we had the Hubble telescope, and I'm sure you now know that there is one more known as the Chandrasekhar that is there already. So all these telescopes are out of the atmosphere so that atmospheric problems should not affect the images that we see. And those beautiful images of the nebula and the stars and the star clusters that we see are all because of these complex type of telescopes. Things changed. Actually, you must realize that there are two or three other aspects. We can't see everything. Light is only one part that we talked of. There is a possibility that information must be coming in other forms or other parts of the electromagnetic spectrum. And for this, then, what was developed was the radio telescope. We have one GMRT, Giant Meter Wave Telescope, that is used to track down from Narayangaon, where you track down a variety of things. That's a radio telescope. Then, as I said, we have reflection telescopes. We have other mechanisms that are also added on to telescopes to make things more and more beautiful. So, this is how telescopes work. There is one more aspect. I talked of the eyepiece. The trouble is, there are some problems with normal single lenses. So, combination of lenses are used to form the eyepiece. So, the eyepiece itself is made up of two, three lenses, and the objective itself may be a combination of one or two different lenses to take care of all the problems that are there in the telescopes to give us the best possible images. And that is how we have looked at the sky and obtained so much of information of black holes and neutron stars and so many other things. Light, my dear friends, is fascinating, and the space is equally fascinating. It is a combination of the telescope and the human intelligence that has given us so much of information. But that's at a great distance. There are things at a closer distance too, and that is the microscopic world. We need to see the microscopic world also. For that, you need a different system. But for telescopes, whenever you talk of telescopes, you must think of four things. How big is the opening? How much of light is being gathered? So the more the light you gather, the better is the image. So the greater the diameter of the system, the better it is. You also need to find out how much is the focal length, because more the focal length, the bigger will be the initial opening that is obtained. I also talked of the magnification, that is the combination of the objective focal length and the eyepiece focal length. And there is one more factor, and that is known as the resolution of a telescope. The ability to see two things distinctly. Many a times, what happens is when you see an object, you see a lot of hazy things around it, and there's a second object with a lot of hazy things around it, and they are so close to each other. That's what happens when there is rain that is there on the on the windscreen, and you have lights on the other side, and you can't see them properly. The ability to see each one very distinctly is known as resolution and resolving power, and that has to be very high. So all these high quality telescopes are designed with these three or four factors in mind, and only then can we get such beautiful images. But then what about those simple binoculars that we tend to get? They also give us some magnified image. And then you put them on your eyes and you see a tiger and you see so many animals and so many things. And there are some numbers written on it. You could have a binocular which is 7 by 35 or 55 by 9 by 22, something of this sort. The combination of these two numbers is what must be understood. And then you will realize which quality of binoculars are good. 35, 55, 28, etc. tell you the angle through which you can see the objects. And the other number, 9, 7, 5, 11, are all the multiple times the object appears when you look at it. So when I look through the one that I have like with me, 7 by 35, uh, that 7 is the image seen is 7 times, and I can look through an angle of 35 degrees. The wider the angle, the better you can look at things, but then they don't appear to be very big. So when you try and look, with 9 by 21, the object is going to appear 9 times bigger, but the angle is going to be restricted to 21 degrees and you'll have to hunt around for it. That is how microscopes and binoculars, I'm sorry, telescopes and binoculars work. If you have liked whatever I have said, please pass on this information to your friends. Next time you use a binocular or any device of this sort, make sure that you understand the logic. When you look at the sky, look at the images that are there in a variety of books, because the telescopes that are around that you usually come across are not really all that powerful for us to see. So enjoy space, enjoy telescopes, look at the world around us, look at the world in the sky, and enjoy life. Next time we meet, I'm going to come to another area of light and we'll relate it to some of the information that we've already talked about. Now we are moving ahead, so we'll try and combine things together. Till we meet again, Namaskar.